So today, what I'm gonna talk about is I'm basically doing DFT or some sort of many-body computation, which can be relatively easily combined with DFT, like a DMFT, for example. But in this particular study, I'm just doing DFT, mainly because DFT simply seems to be enough, as partly pointed out the previous speaker. So, so the purpose of my talk, my study is basically we want to look into more details of the electron structure of this 135 compound. And our main interest here is the Van Hove singularity formation in this material, and also the interaction strength in this material. All right, before really starting, let me start by thanking my collaborators. This work, basically all the works, all the results that I'm presenting today is basically published in these two papers. And Myung, who is now in Samsung, and he is the main driving force of this study and all the computations, basically. And the Sang-Joon, when the Myung left my group, Sang-Joon tried to take over, and he's mainly contributed this, the second paper. And the Sung-Bin's group and Yong-Baek's group in Toronto, we worked together from the very beginning. And as you probably know, their background is very different from mine. So their main contributions, we eventually separate these two studies. It's published in this paper. But today, my talk will focus on these two papers. All right, I don't feel that I need to repeat all the details about this material here again. But let me just, one point I'd like to point it out. If we look at this material, there's two different types of antimony inside, okay? So one is in plane, within the plane, with the same plane with vanadium atoms. So let me call it the antimony, in-plane antimony. But there is another antimony which is an out-of-plane antimony, which is the, let me call it the out-of-plane antimony. Like this, you can see clearly, it's very obvious. And many fascinating phenomena has been reported already, and we try to understand. We have listened many outstanding talks on this study and in this workshop and for the last 2 days. And as we know, this is, I don't want to spend much time in this page too, but this is the Kagome lattice. If we go toward the let's say strong coupling limit and localized moment limit, then we will have many fascinating physics we can probably find out. But in this particular system, we are not in this regime, but we almost certainly we are somewhere here. Let me call it weak coupling limit or band limit. So what it practically means to me, I mean, the person like me, is we don't need to resort to the such a more advanced technique like a dynamic combined field theory, but we can simply go with relatively simple or standard approximation like a GGA, gradient, generalized gradient approximation within the DFT framework, which is actually what I've taken in my current study. So this is the early band structure calculation result. There are a couple of nice papers out there, but I just took these two papers just for the nice presentation. So this is the so-called pristine structure, band structure, okay, pristine band structure. This is so-called charged after the charge density wave order occurred, which means an inverse Star-David structure. They compute the band structure, but they unfold. It is possible to unfold band structure, even if we lose some weight, but it's reasonably well working. So you can compare. It's not very much different. Of course, they try to highlight some Van Hove singularity at the Fermi level slightly shifted and some changes around the Fermi level. But overall, you can still identify the Dirac point, for example, and Van Hove singularity point also. This is another version, probably is better to be highlighted. And you can see the Dirac point and Van Hove point, but I like to focus on Van Hove point here. As we can see, let me, in the first part of my talk, let me just call this a 3 Van Hove singularity points, okay? Maybe it's better to call this a 4 points, but I'm just following this paper, early paper. So I can see 1, 2, 3 Van Hove points around the chemical potential. This is the thing that we learned from the early papers. And everybody, I think, agrees that the Van Hove singularity can be important to induce many exotic types of instabilities, okay? So, and this material is believed to be locating somewhere here, and that's probably and likely the driving force of so many exotic phases in this material. So this is an early summary. I know I admit that I missed many of outstanding recent papers. In this page, this particular page I prepared in very early stage of my study. So, but anyway, this I think still is quite exciting summary of what is going on in this material. Already quite complex and quite fascinating. And this is a temperature scale, and we have short-density wave and this very intriguing, possibly broken time reversal symmetry phase, and nematicity and superconductivity and so on and so forth. And as we have discussed during this workshop, there are many controversies and many issues and debates against this and another. And these phases, for example, like a TRS phase, and also superconductivity. We had such nice talks in this workshop. But okay, so this is quite complicated, and intertwining nature of these phases, I don't think we have a clear understanding yet. That's the underlying of motivation of my study, of course. So now, so let me here, I don't want to spend, once again, I don't want to spend much time, but let me try to introduce some inspiring, to me at least, inspiring earlier theoretical works. It is quite interesting to me that already 10 years ago, the people, great people, provide some very insightful theoretical studies. So, first example is this. So this, I'm not an expert on this kind of tool. So let me just briefly describe what they achieved. So they try to solve this simple Hilbert model, and they decide to take a single orbital, and they took a variation cluster approach. And what they did was in this approach, they can compute some thermodynamic quantity, like some potential. And as a function of U, and they can compute, for example, the instability. They can examine the instability of superconducting pairing, which corresponds to this area. This is their phase diagram. It's this one-dimensional phase diagram because they don't have the V term here. So basically, it's a kind of line. So they focus on this particular site, which seems quite intriguing. So they eventually suggest this. I'm not saying that, but I'm not saying that this model and this study is realistic to be relevant to this material, which is not very clear to me. But anyway, D plus ID is still remains as an, quite plausible candidate for, thank you, even today. The next study I'd like to show you is these two papers. which seems quite similar, at least the model level. It's extended. Okay.
The disordered magnetic insulator, is that a non-magnetic insulator?
You mean this one?
Yes.
Okay, so I don't, this one is represented by this. So I don't fully understand what they mean by this, but this is not, doesn't look like a non-magnetic.
Okay, so you're
saying,
saying...
it's a magnetic disordered insulator, they claim. So what I understand is something like an, local moment, it's disordered.
Yeah,
what
I mean,
my impression.
Okay, probably means there's no long-range order.
No long-range order, yes.
Okay, thank you.
These two studies seems to me, is quite similar. Single orbital and extended Hove model, that's key difference from the previous one. And they are doing FLG, but as you can see, their phase diagrams are very different, at least to me. For example, I remember we have seen this phase diagram in the previous talks. We don't see any superconductivity here, but here we have S-wave superconductivity and D-wave superconductivity. So it must be a bit or fairly different. The only differences that I can identify from their paper is this is a patch FLG, and this is a singular mode FLG. I'm not a good person to distinguish these two techniques, but anyway, this is a thing that I can take from the outstanding previous papers. But it is anyway quite amazing that as far as we go to the Van Hove filling, and based on even such a very simple model study, we can create many instabilities. And then those papers before we found these materials, and after the discovery of 135 material, of course, there are several outstanding papers. Let me just take two of them. Here we can see some of our members of this, and organizers paper. Yes, and now we know what's happening in this particular material, and our theorist, our classic theorist, revisit seems to revisit this material with a similar kind of model, and it's worth looking at again. So, so this paper is RPA paper, not FLG. Yasir is here, so maybe we need to ask to Yasir for the more detail. But for me, is once again quite interesting by starting from this extended Hove model and RPA, relatively simple computation. They found these type of very exotic superconducting phases stabilized, and my impression is that they mainly focusing on this phase, which they seem to believe is more relevant to this material, particular material. Okay, that's the first paper. The second paper is about the charge order. They call it nematic chiral charge order with this charge order. Well, I didn't put any result here, but what I want to emphasizing what was most appealing to me, to myself, was the when they try to understand the superconductivity, can you see this index? They seems to take a two orbital model. Okay, you see this XZ and YZ, XZ. This type of two orbital model means two Van Hove singularity. The two orbital. So yeah, so at least they need to consider two orbitals. Okay, but in this particular case, this paper, when they try to explain or understand this chiral charge order, they seem to just satisfy with one single orbital, which they can, you probably cannot see quite clearly, but they mentioned just the XY orbital band structure. So as a band structure person, this is quite informative and inspiring. And finally, of course, we know this kind of patch model. I think there are some introductory remarks in the previous talks about the patch model. Many papers actually based on patch model. Patch model is mainly focusing on one particular K points, which is of course the Van Hove points, and around that region, and they can examine the instabilities. And once again, we can see many instabilities can be stabilized, okay, realized, including imaginary CDW. Of course, we cannot talk much about the quantitativeness in this kind of approach, but it is quite clear that as far as we are focusing on the Van Hove singularity and we consider the electron correlation, many exotic phases can be stabilized in real material. And this paper is also very intriguing to me. I mean, for example, if I read carefully about this paper, they wrote something like this. So once again, they mention about the two orbitals when they are trying to understand the formation of charge order. But when they talk about the higher order Van Hove singularity, which is different band actually, this is an RP study mainly. So they are referring to different orbital, okay? So with these outstanding previous studies as my motivation, we decided to study our own computation. So the motivation is as follows. To me, it seems quite clear that some exotic possibilities can be stabilized at around the Van Hove filling, which includes this unconventional superconductivity and TRS breaking cutoff spin-over. And partly due to the controversial experimental reports and limitation of theoretical tools or models, many key questions to me still remains unresolved in regard to the, for example, characteristics and intercorrelation of each phases and why. Of course, we cannot directly attack to these big questions, but as a DFT person, we define the following questions. We are having the minimal model question about once again, the Van Hove singularity formation, the right structure around the chemical potential, why and what is the driving mechanism for the formation of those structures. And relevant parameterism is also a right question to be asked and can be attacked by such method as DFT. And of course, some other details, which is, for example, material dependence and so on and so forth. So in the first part of my talk, I would like to focus on the formation of 3D Van Hove singularity structure and realistic parameter regime of U and J, Hund J, and extended Hubbard model V. So let me start from the very beginning, I mean, from very basics. So this is my material. And if I look at carefully, the first thing to be clarified at that time we believed was the, if I look at this carefully, vanadium atoms, the local structure of vanadium atoms are not well aligned. What it means is that just looking at the structure, these octahedra are not well aligned along the same direction, right? So we need to define the local axis first properly, okay? So if I just take this is Z direction and this is X direction, this is Y direction, it can be misleading, okay? So what we found is that there is a well-defined way to define, okay? So what we take is, we took a Z direction along this in-plane antimony site. This is vanadium and this is in-plane antimony. And this is out-of-plane antimony. And this is my x-axis. So z-axis is exactly along this line, bond line, but x-axis is a slightly offshoot. But this is we believe is best. And y-axis is also slightly off axis, but it's not very much. So it's basically, you can believe this is z, this is x, this is y. This is quite strange because in the sense that if I take this local axis, then my z-axis is in the plane, okay? So that's the thing. Looks strange, but it's probably better. In the sense as following sense. So this is the orbital resolved band dispersion following, and my orbitals are defining the global axis. This is redefined orbital axis, and I draw the same band dispersion, but orbital characters are of course different. The key difference, what we believe important, is this endpoints. We know the pure type and mixed type, we have listed in several talks explaining these features. But basically at M1, M2, M3, the orbital characters should be same, right? But if I choose to this global axis, it's clearly it's different. For example, the M1 and M3 are same, but M2, the orbital characters are really different. But if I take this local, properly defined local orbital, or local axis coordinate, then it is really well defined. So I think, as far as we are caring about these orbital characters, this is important. And another important, so based on this local orbital character, we try to start to analyze orbital characters. One important lesson I found is this is probably better to be named the Van-Hove 1, Van-Hove singularity 2, 3, but at that time, because of some reason, we call this saddle point 1, saddle point 2. But anyway, this is Van-Hove points. So the closest Van-Hove points to the chemical potential in this system case is this yellow color or orange colors. And we found, based on this axis, this is a single orbital character, which is more than 70%. So I think it's a kind of important because it justifying single orbital studies, and which is including the patch model, which is well-defined single orbital characters, and which is closest to the chemical potential. Okay, so as you can see, the band structure, overall band structure is the same, but the identification of the orbital characters can be different, okay? And now let me look at more details of the other Van-Hove singularity points. Okay, so the first Van-Hove point here, it's a magenta color, is mainly YZ, XZ characters. Okay, it's different. And I like to more focus on this third Van-Hove point, which is not very far from chemical potential. But the important, interesting point is that this third Van-Hove point is a sizable portion of out of antimon P. This is not in plane antimon P, but the out of plane antimon P. Yes, this is quite interesting to us, and it is even more than the orbital components. So we decide to focus on this. What's the role played by this out of antimon P? So this band, gamma point band, dispersive band, was pointed out with yesterday's talk in the Stefan. But this is in plane antimon. But this out of plane antimon role has not been, as far as I know, we focused on. So we were fascinated by this these third Van-Hove points, and it is actually So let's what we did was as follows. This is a band structure that we have found, and we tried to construct T2G only type bonding model, which is what we tried to use was the straightforward maximally localized Wannier function technique, which is kind of standard to construct the type bonding Hamiltonian. We can just construct the T2G only type bonding model, and we draw, just diagonalizing this Hamiltonian, we draw the band structure. It's something like this, okay? So if I'm, well, it's of course very different. This is a full band DFT. This is a 3-band type bonding. But if I've just focused on this M-point Van Hove singularities, well, this guy, okay, the Van Hove 2, saddle point 2, is fairly well reproduced. So if you can work with, if you want to work with this guy, maybe this or single orbital model, maybe okay. But I cannot generate, for example, the Van Hove singularity 2, I'm sorry, Van Hove singularity 1, which cannot be reproduced. It looks like this, okay? So we decided to put the EG orbital too, but still, I cannot create other Van Hove singularity points around the chemical potential. Here is something, but it's around this point. Still, these bands doesn't go like this, but it still remains something like parabolic. Okay. The main differences that we created by including EG bands is something like over here, which is flat band region. But Van Hove singularity point is not pretty much enhanced. So as soon as we put antimon P, which is actually the out-of-plane antimon, on top of T2G only model, we start to get these 3 Van Hove singularity points, okay? So it is really, I mean, this out-of-plane antimon P is really, seems to be really crucial to generating the 3 Van Hove singularity structure around the chemical potential in this material. And now finally, we want to put all these T2G and EG and antimon P. Then this band structure looks quite similar with this full band DFT result. I can also have this 4th high-lying Van Hove singularity, which is not here, so which seems to be related to the EG bands. But anyway, at this time, we more focus on this 3 Van Hove singularity points structure and the formation of those structures. And, oh yes, please. No problem. Oh yeah, it's crucial. I mean, the out-of-plane antimon P is crucial.
So you said in the top right that you're able to capture the singularities, but it kind of looks like there are just like this orange, yellow band, TXY. Looks like it's versus.
All right.
It looks like it's the same karyotype for gamma and K. So is that actually a Van Hove singularity?
This one. Yes, yeah, it's a very good point. Actually, we carefully look at this band, the yellow band or orange band, and along another direction, it should be going like this, right? Yeah, it is. It is. Yeah, it is a Van Hove singularity. Yes.
So if this band structure cut, why does it look like it's dispersing, but it's going up with gamma and K?
This one. At that point, I'm not quite clear. I mean, it's not quite clear to me. Right.
So if I look at this plot, if I look at this band structure, not along the cuts, but it's the contour plot, you can see that this band is probably a saddle point.
Yeah, yeah. As the feature, a saddle point feature is going like this and going like that.
So is it that the concave down direction is constantly along K, it's on other direction?
I'm sorry. So your point?
Yeah, I'm just trying to understand. So as I go away from
Mm-hmm.
in one direction, where I'm concave up, one direction, where I'm concave
Yeah.
plot it, gamma M and K concave up.
Mm-hmm.
The question is, does that mean that the concave down direction is neither along gamma M or K?
You mean this one, for example?
No, I'm talking about top right.
Top right.
Yeah, that's top left.
Top right. Top right. Okay.
Yes.
Yeah.
So, yeah, the yellow band, if you go away from M, this plot is concave up with gamma M and K.
Mm-hmm.
Right? So my question is, from a saddle point, there should be a direction where it is concave down. So if that direction is neither gamma M or K,
So Well, we didn't look that carefully because this is a kind of, step-by-step formation of band structure. So, well, so basically we didn't pay much attention to this slight upward direction, I mean the change, because it eventually going down and it looks like the DFT like. So I don't know, I mean, so, but we did check. There's some other, I mean, the three-dimensional feature is still maintained and quite similar with DFT. But yeah. And any other question or comments? All right, so this is the one interesting finding obtained. And then, okay, so this is the control of, I mean, for experimentalists, for example. These boundary singularities can behave in different way in response to the structural change. It can be useful or informative for experimental study future. So we consider the strain effect. This is a tensile strain and a compressive strain. This is a hydrostatic pressure we simulate, which means A, B, C axis simultaneously contract. So in-plane lattice decreases along this direction in this figure and this direction in this figure. And our plane lattice parameter always decreasing from left to the right, okay? And what we found here is the boundary singularity 3 is basically behave a bit different from the other twos. For example, especially in here. So basically we can control, I know these kind of numbers for strain is too high, but basically we can control the relative distance to the chemical potential we can control. So probably and hopefully we can examine the role of boundary singularity can be controlled, and we will see something happens, then it would be very exciting. All right, next question is about the interaction strength. Okay, and we found an interaction is key in the previous study, is very important to stabilize exotic phases. So what we perform is so-called constrained RPA scheme. In a nutshell, let me just very briefly introduce this technique. So basically we can, I mean, the DFT people have long history to compute the screenings in solid based on the RPA level. The most well-known case is a so-called GW method. It's W, screen Coulomb interaction, is basically computed within the RPA. So, the Baer-Coulomb interaction is screened by epsilon or epsilon inverse. So V becomes W. But this is an RPA, which we can do. But what the constraint RPA is, idea is very simple. So constraint RPA is basically developed to provide the Hubbard U or Hund J or so. So we separate our space, like a correlated subspace, let me call it a D space, maybe referring to D orbital, and all the others, let's say rest space, R. So my polarization is basically composed of these polarizations, okay? So my electrons can polarize from here to there, from here to there, from here to there, but also from here to there. So all things are my polarization, but we can distinguish depending on which subspaces this polarization is happening. And then epsilon is defined in this way. So finally, by having these polarizations of R, is by defining in this way, we can define this epsilon in this way, and my U, how about the U in this case, can be computed from the Baer-Coulomb interaction by multiplying this particular epsilon. Okay, this is the idea, is like 20 years ago, and we have been using this technique. Okay, which is the yeah, it's pretty nice and kind of frontier technique nowadays. So this is very nice. I like this method very much, among a couple of other choices. One of the reasons is as follows. The more screening channel removed, the larger effective Coulomb parameters should be obtained as expected. And we can do this because we can define this correlated subspace as we like, okay? So here's the result. So if I remove all the screening channels, which should give rise to the Baer-Coulomb interaction, which is such large numbers. This is a Hubbard U, and this Hund J. This is a second nearest, nearest neighbor interaction V. And if I remove screenings from vanadium D and also antimony P, and I can have all different choices, okay? And you can see systematically these screening channels more and more get involved, then the U values getting reduced, and J values and V values. So, if you are working with a D-band only Hubbard model, probably this value is probably most relevant to your model Hamiltonian value. And if you're working with a DP model, for example, then you should probably take the value around this value, okay? So this is actually, there is a one DFT plus DMFT paper published in 2021, and this is, they without any information or computation, they just decided to choose just around 5 EV value. It is consistent with, happened to be consistent with our result. Okay, so now look at our material property. So I think one of the most interesting points here is the U and V ratio, okay? Because in the previous model study, they just took an arbitrary value or some ratio they need to fix. So here is a result. We need to compare this to, well, yes. So finally, we just put, this is not very serious pointing, but it would be very interesting to see. I mean, we decided to take D-band only Hubbard model value, U value and V value. Of course, this is not, I mean, we should not be confusing about this value itself because, I mean, the patch model and single orbital Hubbard, extended Hubbard model value should not necessarily be identical with this value. I admit that, but this is the, among these choices, this is probably the closest value to the previous studies. So if I put my values, U and V, here in this particular study, they have no V, so I just put U values 0.9, somewhere here. Well, as Carl superconductivity sounds good, okay? And this study, unfortunately, they fixed the V value is 0.3 U, so I cannot make fine tuning, but if I just put my U value somewhere here, which sounds good, okay? But if I go to these two papers, I'm falling into the ferromagnetic solutions. But anyway, once again, we didn't mention anything about this in my paper, but it's interesting to see this kind of picture. All right, another important and interesting point here we found from our CLPA calculation is that, let's focus on these values, okay? So we start from here. If we remove all the P screenings, P orbital screenings, and if we put, so this is out of plane antimony P screening contribution, we can compare by this number, that number. So what this number, I mean, this is a small change, and this is a large change. What it means is that, yes, please.
We're running out of time.
Oh, I'm sorry, okay. Running quickly, okay. So this sizable change means the screening comes from the outer plane P orbital is sizable, okay? So the outer plane P orbital plays important role not only for the formation of 3 boundary singularity structure, but also for the electron screenings. It's quite large numbers. Okay, this is really the final part. So now the Myung left my group and Sang-Jun joined, and we still have we feel that still remain a couple of remaining questions out there because we didn't consider the A-side dependence. But in the meantime, there are many papers addressing the material dependence. I mean, A-site dependence, I cannot go over this page, but you probably know better than myself, and the material dependency. Some notable and qualitative differences we can find out. And if I look at the boundary singularity points, comparing these three materials, which is really different. This is a system case that we focused on to this point. But when I go to the potassium or rubidium, it's really different. Most obvious case is this boundary singularity 1 and 2. I'm sorry about this color. It suddenly changed because this different paper, different students. But anyway, it says 1, 2, 3, 4, but 2, 1, 3, 4, 2, 1, 3, 4. It's different, okay? So because I have almost running out of my time, so let me just go quite quickly. So we want to focus on the chemical effect. I mean, is it really effect coming from the chemistry or coming from something else such as structure? So we've decided to fix our structure from potassium or rubidium or cesium, but we also change our elements from potassium, rubidium, cesium. So if I look at the potassium and potassium structure, this is really the potassium material. But cesium in potassium structure, which is a potassium structure, but chemistry is cesium, coming from cesium. But what we can see from here is basically a structure effect is relatively small, but this boundary singularity order, at least the order of boundary singularity, is mainly governed by chemistry itself. Okay, so we call it the chemical effect of the boundary singularity structure. So we once again monitor the structural change and how much it can be controlled from the experiment. For example, in this case, we particularly change the singularity parameter. And once again, you can see these two boundary singularities not very much responding to the external structural change, but these two are pretty much. That is actually, main reason is, once again, the out-of-plane antimon P, which is a sizable portion in 3 and 4 boundary singularity, but not in 1 and 2. Okay, so this is my summary. I don't want to repeat this statement again. Thank you very much for your attention. Yes.
Questions for the audience? Yes, Julian.
Screening of the column interaction. I was wondering, do the in-plane antimonies contribute in any way to the bands near the Fermi level? Because I think your plot with the orbital weight just was total antimony, right?
Yeah. Well.
Yeah. So this is. So how much of this green is in plane and out of plane?
This I don't remember the number, but it's mostly in plane antimony. Yes.
It's mostly in.
Yeah. That's what we, including ourselves, and people noticed and discussed is, as far as I remember, this is the only feature that they discussing about in this material. So this is in plane antimony.
I see. So the gamma pocket is in plane, and saddle point 3 has some contribution from out of plane.
Yep.
You discussed the CRPA results in view of removing states from the tie binding model. You focused mostly on U and V, but I also observed that the J was
yes.
actually not really screened,
Right.
such that in the D only model you have a very large J, which is actually larger than U over 3.
Right.
So do you trust these results, or
well?
Or I mean, because that would mean that, if I interpret it correctly, that the U prime, the
right, I understand
interorbital U would be negative.
U minus 2J should be U prime, right?
Yeah.
Well, that's a very good point, actually. This is, well, yes. To me, this question is about how reliable is RPA techniques and so on and so forth. And there are many discussions, of course. This is a 20 years old idea. And nowadays it becomes one of the standard method and many discussions. Well, Of course, it's certainly limited capability in fundamental level and also practical level. Well, so if you ask me, do I trust this number, for example? Well, yeah, I admit that this number is too large. I mean, of course, the U minus 2J is within the perfectly cubic symmetry, but even if not, so it should not be that large. But well, at this particular material and only with this value, I don't know. I mean, I cannot simply say I don't trust this because it's too large. Well, sometimes CRPA doing such a nice job that they give rise to negative effective U value. Sometimes that's, I mean, I should not say correct, but it's physically meaningful. I mean, if you go to the, for example, the potassium, potassium-doped fluorine studies, they are really finding some indications and putting this negative attractive U value, they try to explain some superconductivity, I mean, minor correction. So I cannot simply say that this is, to me, yeah, I agree, this is too large, my first impression. It could be overestimated because matrix element effect and so many technical issues in there. But basically, CRPA is a kind of, I think it's kind of one of the state-of-the-art techniques. So we should not simply discard this number. So it's my comment, okay.
Time for question. Yeah. So in one of your slides, you flashed your other work.
I'm sorry.
In one of your slides towards the end, you flashed your other work on nodeless nodal superconductivity.
Okay.
So my question is, are you able to compute the spin fluctuation mechanism, unconventional superconductivity with your constraint RPA?
I'm sorry.
like
This is
the
just experimental results. I tried to summary experimental result. Some papers, if you look at these papers, I forgot. I mean, I cannot recall all the details, but yeah, some experimental reports talk about the nodal.
Right. No, my question was, are you able to use your technique to compute unconventional superconducting pairing?
For me, no.
No. Okay.
No, I'm just, yeah.
Right.
Many exotic superconducting possibilities already suggested out there. So.
All right. So let's thank the speaker again and let's close the session.